I'm good so far.
Okay. So yeah, so I'll start with the presentation. So what is the deep learning for NLP? If we take a classical NLP pipeline, then we need to write for each and every specific task. There needs to be different pre-processing steps. For example, for pause tagging, you need to write a different pipeline. For say sentiment analysis, you need to write a different pipeline. But the advantage of using the deep learning model is it can be unified into a single ML neural network model, and we for a specific task we just need to fine tune only at the output layer at the end. So this uniformity is one of the major advantage of adopting deep learning based NLP techniques. So if you take the history of neural natural language processing, so we started the neural language models were initially started in 2001, and in 2013 word embeddings like word to vec became popular, and then it was like RNN encoder decoder, which also learned sentence representation had become popular, and they were trying to adapt these models for doing various tasks like language translation, and it was met with the limited success. But after attention models came, there was a major breakthrough. The attention models was the one related to transformers and BERT, and this BERT comes under the class of pre-trained language models, where you can just create a huge language model once by training on Wikipedia, and after that you can adapt it to multiple tasks. So that's what we'll be seeing. And to your overview, like we'll be seeing how this BERT evolved from a basic neural network. So I'll be going through from the initial how the neural networks works, and then I'll be covering like RNNs, then all this thing to from the basics. I'll be covering till the transformer. So if you take the first model, the neural network, you can think of it as a black box that is trying to learn a functions that maps the input vectors to the output vector. So the training model is as follows. So we give the input to the neural network, and there are multiple hidden layers, and the neural network comes up with the predictions, and then we compare it with the true target value and compute what is the difference between this target and the actual output given by the neural network, and we compute the difference in terms of a loss function. That loss function can be a simple MSC for a regression problem, where that computes like what is the how by how far my network has missed, or how bad the network is. So uh, yeah, then once we compute the loss, there is an optimizer that tries to convert the gradients, which is the derivative of the loss with respect to individual weights, and then it computes the new weights. These new weights, these new weights are now present in the neural network, and now again the input is given, and again the output is computed. This process repeats till the weights are adapted, and the neural networks predicts a very close output to the target. So we want to minimize the loss of the neural network. So that's the overall objective. For doing that, we try to see like how far our predictions are from the true values, and then we find what is the in what direction I have to move, that is given by the gradient or the derivatives of how is the loss function with respect to each of the individual weights, and keep adjusting the weights till the neural network performs good. So it be in at a high level, we can think of the neural network as just a black box that computes the output from the input, and it is trained with known input and output pairs, and it creates during the process of training, it approximates that function that predicts what is the relation between the input and output, and we can use that function for new inputs. So that is how neural network operates. So even if we don't get to into the internals of the neural network, it is good to understand at a high level, at a black box level, how it does, because nowadays, like most of the actual working is abstracted by good libraries like TensorFlow or Keras or PyTorch. So this is what at an API level is happening. So once we have this neural network, like how we compute the word to vec or word embedding. So here we are given training examples of the nearby words. So if you take this for example, there is a window of length 5, and we compute like what are the co-occurrences of the words in that window, and these are given as the training examples, and we need to predict what is the context, what is the word from the surrounding words. And once the neural network is trained, thus this neural network is capable of taking the surrounding words and predicting what is the actual word, or vice versa. It can take a particular word and it can compute the surrounding words. So there are two models, and we actually discard all other things and only take the hidden layer, and the hidden layer actually learns a representation that computes the word to it. The hidden layer learns the word embeddings. So these word embeddings will be learned in such a way that words that are near to each other will have minimal distance. So if you compute distance and of these word vectors, it will be operating in that manner. So this is the output of the word to vec, and you can see that it captures the intricacies of the language, like word analogy, the famous man, king is to man, and then queen is to woman, or it can uh, calculate the superlatives like slow, slower, slowest, or it can even identify the capitals of the countries. So plurals, all these things can be learned, and RNNs are just okay, now we have a word representation, but to go to sentence representation, we take advantage of the RNN. RNNs are just neural networks which are unrolled in time. So we have do back propagation, and so the output is fed back into the hidden layer. So what happens is this recurrent neural network becomes capable of identifying sequences also. So in that way, it can learn the sentence representation, and by learning the sentence representation, it can predict what is the nearby words. So it can compute on language model, like even a sequence of word, it can predict what is the next word. And yeah, this was useful for doing the language translation, but still there were some problems in learning long-term dependencies, and for that we were using attention model. So in RNN, only the final state is used to decode, but whereas this attention models capture the individual hidden representation, and gives a weightage of all the individual hidden representations. So that's how this attention mechanism is useful for inference. So actually, this the Zoom meeting is about to end. So actually, can we meet on this Google Meet itself? Hello.
Sorry, what you are asking? Come again?
Yeah, actually, the Zoom meeting may end in another 5 minutes. So, is it fine if we reconnect on the Google Meet after
Yeah, yeah,
after
yeah.
a,
Sure, 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 sure.
uh,
So let's
uh,
continue for the next 5 minutes as well, and then we
yeah,
can join there.
yes, yes. So, the attention models can capture the relationship between the words. For example, we want to translate from English to this French language. So what we are doing is computing the embedding of each of the word similar to word to back. So these are non-contextualized representation, and what will be happening is there is a self-attention mechanism that computes like how these words are related to each other, that is captured by the self-attention mechanism. And there is another kind of attention mechanism called encoder decoder attention that specifies like how much weightage each of the word in the target must be like how much importance should be given to each of the word in the source. So that is computed by this encoder decoder attention. Again, we have another self attention layer in the decoder itself. So the idea of this self attention is it captures the relationship between words within the language itself. So within English language, how one word is related to another word, and similarly for French also. And this encoder decoder attention captures how one word in English is related to another word in French. So that is captured, and with all these things like we can create a encoder decoder architecture with the transformers that can take in the input language, and it will compute the self attention, that is it is a representation of how the words inside the language are related to each other, and then we pass it to a feed forward network that creates the final embedding, and then that embedding is fed to the decoder. And in the decoder, again, there is a self-attention layer that computes the dependencies within the language. The encoder decoder attention computes like how words in one language is related to another. Then we get the words in the target language. So if you take only this encoder part alone, what this encoder is doing is it is trying to create a richer representation of the words, and it is trying to create a richer numerical or a vectorized representation of each and every word, giving importance to the context. So if you stack multiple decoders, then we get the BERT model. So here we see that if we have this transformer layer, and if the transformer layer is trained on a huge corpus like Wikipedia, then it is learning the BERT language model, which is a rich representation similar to Word2Vec, but it includes the contextual thing also into account. So once we have this language model, then it becomes easy to this is the BERT model, which is pre-trained. Then it becomes easy to adapt to our domain-specific task. So that's yeah, that's the idea. And to summarize, we saw that neural networks can encode individual words. So RNN can encode the sentence level, and we for longer sentences, there are changes to RNN like LSTMs, GRUs are there. And if you have two encode RNNs or LSTMs side by side, then they can act as encoder and decoder of any representation. Like It can be English to French, or can even do image caption, convert image to text. These kind of encoder decoders are possible. And if you encode everything into for the entire sentence at once, it loses the context. So what we do is we selectively pay attention to what are the inputs while that we need to focus on while we are translating that particular word, and that is called the attention mechanism. Later we can get rid of that RNN mechanism and use only the attention mechanism. So that is the idea behind the transformer network. And we use self attention to capture the dependencies within a language, and we use encoder decoder attention to capture the dependencies across the language. So that's what.
Yeah, Arvind. Hmm. All right, like this is good from my side, Arvind. With the interest of time and
Okay.
this Zoom link will gonna expire, so I think I'm good so far, and I don't have further question. This demo was good to me, so I'll
Okay.
provide my feedback to Sakshi, and she will connect with you.
Okay. Sure. So you want to connect on Google Meet now?
No, I think that's not needed. I'm
Uh,
actually good, whatever I need.
okay. Okay.
Do
Fine.
you have any
Okay.
questions for me?
No. Any feedback?
No, it's all good from my side. Nothing specific. It's just that the only thing I would say, if you can be more sound more little excited, and
Okay. Okay. Mm,
there should be a variation of the pitch,
mm,
like,
mm,
it's not like a same pace all the
mm,
time. Sometimes we are just increasing it a bit, sometimes decreasing. So that
mm.
variation, if added, it will be more impactful,
Okay. 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 Got
so
it.
that
Got it.
learners don't feel little monotonous, because as you know, learners are new, and they feel like too much of information. So if
Mm,
you speak with some excitement, something, high low pitch variations, it will
okay.
be
Okay.
it could become